All right. Good morning, I guess. So I'm going to tell you a little bit about visual computing in general, and then I'll mostly focus on my own work, just like any good academic, very self-centered. But I really want to give you a sense of the richness of this field and its presence at MIT. So what we call visual computing is anything that has to do with images as input or output, whether it's computer vision, 3D computer graphics, et cetera, et cetera. And it's really an important area, partially because most sensing and perception are visual. I mean, essentially, the two things we're pretty good at measuring are electrons and photons. And so whatever you want to measure, you have to somehow turn it into either something visual or something electrical. And so as a result, you end up with tons of areas that you may not expect that involve visual computing. And at MIT, we have a ton of people working on this, especially at CSAIL, including on vision, deep learning, medical imaging, computer graphics, et cetera, et cetera. And I'll give you a few examples outside of my group, and then I'll focus on what we do, which is more focused on generating new images. We do a little bit of analysis, but I mostly like to create new images. But I want to advertise the work of my colleague, Sarah Beery, who does computer vision for biodiversity. And I think this work is very exciting for two reasons. First, the applications are incredibly important. The health of the planet and its biodiversity are really at play these days. But I think the other reason why it's really important is because this is the type of applied computer vision that forces you to really develop solutions that are robust and can be deployed at scale. And so I think it's really computer vision in the wild, both in the sense that she's really studying wildlife, but also because it forces you to go outside the laboratory and deal with all the problems that you have when you need to confront reality. And so in general, she's interested in monitoring biodiversity and detecting changes across space and time, mostly using cameras, huge networks of cameras, and computer vision. And as I said, it really requires to scale up computer vision because of the number of cameras involved, the types of environments, the differences in hardware. She does a lot of hands-on collaborations with people in the field, always useful to confront yourself to reality and real users. Because of the need for data and sometimes the lack thereof, lots of work on using synthetic data to help scale up methods involving combining multiple modalities, and lots of challenges with adapting methods that work in a given environment to new environment, new conditions, et cetera, which is really a global problem for most AI methods, where you train them with some conditions and then you try to deploy them in the real world, and the real world is different enough that life is difficult. So, and just to give you a sense of how general I think her skill and her methods are, I was talking the other day with someone who's interested in monitoring electrical power lines and equipment and all this, and I told them, you need to talk to Sarah, because even though she focuses on animals, I think all the know-how that she has and the method that she develops are also relevant to things like inspection for man-made equipment. And even faster, we have Paulina Golan, who works on medical imaging and extracting knowledge from a combination of images and other modalities, and really trying to do work that relates these, in particular involving a lot of so-called contrastive learning, trying to figure out what's related, what's similar, what's dissimilar, both within images, within text, but also across text and images. All right. Now let me tell you a little more about stuff that I actually know about, which is stuff I've been involved in. So as I said, I'm a 3D graphics person and also computational photography, and I do a tiny bit of vision. I'm lucky that some of our work has had some impact in industry. We have a lot of algorithms that are in Photoshop and Lightroom, in Android phones, used at Industrial Light and Magic. And I'll give you some sense of some of that work and why it may be useful. Surprisingly, even though I'm an image person, I found myself doing a lot of work on compilers because, as you may know, one of the big challenges in AI these days is really performance, right? AI is so hungry for computation that you really have to care about how performant your code is. And it's not just a question of, is the hardware fast enough, but also, are you making a good use of the hardware? And so this has put a lot of pressure on the development of new compiler technology that can, take human code and turn it into something that will run really, really fast on modern hardware. And for example, we developed this programming language and this compiler called Halide that are specialized for image processing. So it's really focused on, in general, multi-dimensional arrays, but really originally motivated by the case of images, that allows you to compile code that runs really, really fast on modern hardware at a fraction of the cost in terms of programmer time compared to previous solution. So, one of our flagship examples is we had this code that was in use at Adobe that took one of their top programmers 3 months to optimize. It's not even developing the method. The method was already developed. They had a piece of reference code. And even though the code existed already, it took that person 3 months to optimize. And the original code was only 300 lines of code. So it's not even a huge algorithm, but just figuring out the way to make optimal use of the memory system, the parallelism, and all this really took a lot of work. Whereas with our compiler, my colleague Jonathan Reagan-Kelly took 1 day to rewrite the code and got a 2x speed up compared to the code that had taken 3 months to develop. Jonathan is really smart and he's a really good programmer, and maybe that's part of the story. But mostly the tool really makes it much, much easier to explore different ways to map an algorithm to the hardware, and it makes the algorithm independent from the optimization decisions, which makes it really fast to explore, what if I split the things a little more this way? What if I interleave things that way? Hence the productivity gain. And we open sourced that compiler, and we've been lucky that Google in particular, but now also Adobe really picked it up, and it's in heavy use in a bunch of companies. My understanding is that Halide code touches every single video uploaded on YouTube. Pretty much every function in Photoshop now uses Halide. It's made Photoshop for the iPad possible. It's used by Instagram, et cetera, because it's really a huge productivity gain for programmers. And more recently, we've tried to apply some of these recipes to 3D computer graphics and to differentiability. So the two big things you need two of the big things you need for modern AI or performance, but the other one is gradients. I'm sure you've heard of these derivatives. You need to know how a small change in the coefficients that describe your neural network will result in changes in the final output. So that's your derivative. And computing these derivatives automatically is really important because people don't want to do it manually. And if you do traditional, well-established types of computation, then existing systems like PyTorch will do this for you and will do this really optimally. Because essentially, people do some pattern matching and say, you're doing this kind of stuff. This kind of stuff, we know how not only to compute the gradient, but to compute the gradient fast. Unfortunately, that works really well if you're doing text processing, if you're doing 2D image processing, but the kind of computation pattern that are involved in 3D computer graphics really don't conform to that. And so these existing libraries and programming languages did not support differentiability and performance for computer graphics. So that's why, together with people at NVIDIA, we introduced SlangD, D for differentiable, which is a really fast and reasonably easy to use programming language for 3D graphics that gives you both derivatives and performance. And In a way related to Halide, it tries to strike a trade-off between what the compiler tries to do automatically versus what the programmer can still control. Because there are many cases where domain knowledge really helps you make things work a lot better. And so then you can solve problems like this, where you have a target shape or image on the right, you have a reconstruction on the left, and here you're trying to change the 3D shape, the location and color of all these triangles so that it matches the thing on the right. And you can do this very efficiently because at each step you know how to change the vertices in order to maximally improve the match to the target. And in terms of performance, it's at least an order of magnitude faster than if you use something like PyTorch. And it's about the same level of performance that you would get with CUDA, except CUDA would take you like an order of magnitude longer to develop. And you would have to compute the gradients by hand, do a pen and paper derivation. And then not only you have to code your algorithm in CUDA, which is painful enough, but then you also have to implement the gradient in CUDA, which is yet another opportunity for bugs and pain. All right, let's skip this. So that's the underlying infrastructure that allows us to do visual computing really fast. But now I want to talk about this big revolution in image making, which is generative AI and diffusion models. So I'm sure you're familiar with things like ChatGPT, DALL-E, Midjourney, Stable Diffusion, etc., that allow you to type a text, give me an image of MIT professors working hard on departmental service like I needed for slides the other day. And that's all you have to specify. And these models can generate images out of nowhere. And this is really an enormous revolution in the way we deal with images. In my opinion, we haven't had anything that big since the invention of photography. Essentially, this is really a new way for humans to create images, and this is completely revolutionizing the field of computer graphics. So a little more about what's the main technique that underlies these approaches is called denoising diffusion. It's a weird idea at first, and yet it works. So the idea is to look at the process. Instead of constructing images, we're going to deconstruct an image. So let's say we have an image like this as a training input. We know how to deconstruct it by adding noise progressively until we get something that really doesn't look like an image. And the idea of denoising diffusion is to learn the reverse process, where given an arbitrary piece of input noise, it's going to run this backward and give you an image. And if you change the noise, you're going to get a different image, et cetera, et cetera. And because adding noise is easy, it's easy to generate data to train this inverse process. So you just take a database of a gazillion images, you add the noise, and then you train a neural network to go from this image to this image, then from this image to this image, et cetera, until you go here. So that's the way a lot of these models work. I would add a caveat: the latest ChatGPT image model uses something slightly different, but that's still the dominant model, this denoising diffusion. And recently, people, in particular at OpenAI, have been able to apply it to video. Oh, this is not playing. All right. Imagine this is a video. And similar to the, I'll show you real videos we generate. Well, fake videos, I should say. So OpenAI Sora allows you similarly to type a piece of text, and instead of generating one image, it generates a full video. Now, there are a bunch of challenges still. These approaches are pretty slow. The level of control that people have is still limited. If you're not happy with the image that you get, it's not always easy to know how to change the text, and actually whether changing the text will give you the image that you want. And moving all this to video, and especially to 3D, has been very challenging. So let me show you some work in this area. This is some example of generating 3D data from text, some of the early breakthrough work, and you see that it's not quite the level of quality that you'd want. All right. So let me talk about some of these limitations some more and how we've been able to address some of them. So one challenge is personalization. Maybe you don't want an image of a generic person or a generic dog. You want an image of your dog, or you want an image of a given person that you know. And the early techniques to enable this, in particular the work on Dream Booth at Google, in order to do this, they required you to fine-tune your model. So, essentially, you had to partially retrain the model to train it specifically to generate images of, the dog that you want or the person that you want. And anytime you have to retrain your model, the costs are huge, and the stability of what you're doing is also very questionable because, there's always a trade-off between is the fine-tuning helping because it's adapting to what you want, or is it hurting because it's forgetting some of the earlier training? So fine-tuning I always find to be a dangerous proposition. It also struggles with attribution, multiple identities, and things like this. So, as an example, if even if you solve the personalization problem and you ask for a picture of these two Turing Award winners, the model can be confused, and it actually gives you an image of two people, but it's twice the same person because it just gets confused. It doesn't know who's whom in the picture. Essentially, it has no idea of who's whom in the picture. Similarly, you get in trouble if you ask for, I don't know, a blue chair and a red table. Who knows? You may get a red chair with a blue table or two red tables. Well, no, usually you will get a chair and a table. So you may get a red chair and a red table. So these models are not very good at fine-grained correspondence between the text and the images, especially when you have multiple subjects. And part of the problem is that the training supervision is very weak there. The correspondence between the text and the images is pretty low. If you have this picture of a woman and a man standing together, and forget about my red and green stuff, it has no idea. The training data doesn't say where the man is and where the woman is. And that's part of the power of these things, that they still manage to do pretty well despite the weak data, but at some point you get into really limitations. And in general, there's no notion of identity because, and in general, you're not going to describe by text finely enough how a person's face looks like in order to really replicate the identity of that person in a new image. And so our ideas were first to replace text tokens like a man or a pet or a woman by tokens that encode the identity of the person. So, rather than being text, essentially it's a bunch of numbers that are trained, that are learned by the model to encode the identity of a person. So that's number one. And then in order to train this, we're also going to use off-the-shelf, state-of-the-art segmentation and identity encoding neural networks to say, well, given one training image like this, we can decompose it. We know where the woman is. We know where the man is. We can even compute pretty good quality masks. And that's going to allow us to do some training that's much more high quality. And the final thing is that we're going to use that information to regularize the so-called cross-attention. So if you like transformers, that's one of the things that they do, that they really focus on little pieces of an image at a time, or at least in parallel. And what we do in our work is to force them to say, well, when you're looking at the text token for a woman in this image, your cross-attention should be limited to the place where we know there's a woman in the original training image. Similarly, we are going to force the cross-attention for the text token man to be limited in the image to the area where we know where the man is. So we're going to tell the model at training a little more about what we know about the correspondences between the text and the image, and that's going to help a lot. And then, as I said, we're also going to take these individual pieces, send them through an image encoder, which is going to help encode the identity of the person and replace these purely text tokens by something that's richer and that's learned by the network. And you know, the punchline is that it works. Instead of getting twice the same person, our work really manages to get you the two individual people. This is with two other famous scientists, where we really, in our work, we really force the cross-attention to focus on the relevant parts of the image. And I really think that this general approach is going to show up more and more. We really need finer supervision for these image generation models, because just holistically going from one big chunk of text to just an image is just too coarse-grained a level of control. And so I think you're going to see a lot more work like this that just does a lot more pre-processing on the training data to get more structured information and make it possible to use that structure at generation time to have much better control on the image that you're generating. Another challenge with these denoising diffusion approaches is that they require many steps to go from the noise to the final image. It's at least tens of steps, if not hundreds. So, you know, going from this noise all the way to the final cat image, just you have to do it step by step incrementally. And you know, the obvious thing you want to do is, you know, why not cut the middleman and go directly from this to this using something like distillation. You know, maybe once you've trained your slow network, now that slow incremental process can generate a lot of pairs of noise and final images, and just use that to go directly from the noise to the image, train a purely feed-forward use once network for that. Unfortunately, it usually doesn't work, and it's not fully clear why it's so hard to go directly from the noise to the final image. But one observation and hypothesis that we have is that maybe this mapping is just too complicated to be learned by a single network, and you just have to do it a little bit at a time, and maybe you're not doing a perfect job at each iteration, but you get a new chance to rectify the direction, and you'll eventually get where you are. And so the insight that my PhD student, Tianwei Yin, got is that maybe we should try to distill this process still in a single step that goes from noise to the image, but it doesn't matter if the same noise goes to the same image as in the slow process. All that matters is that at the end of the day, we generate the same distribution of images. So, you know, we want to match the mapping, not very specifically one noise to one image. We just want to make sure that the distribution of images we generate is similar to the distribution of images that are generated by the original process. So that's going to give the model more degrees of freedom to say, well, it's a little easier for me if I map this noise to that image rather than to this other image, and my life is going to be easier and I'm going to do better. And the original model is very important because it provides us with the ability to compute that notion of distribution and to know if the probabilities that we're matching are right. And I'll skip the mathematical details, but this is an important insight from previous work, that you can turn these denoising models into essentially a way to get a sense of the probability of each image you're generating. So that's the main idea. You know, just relieve the constraint that the mapping should be the same. It gives more degrees of freedom to the model, which is good on the one hand because then the task is easier. On the other hand, more degrees of freedom can make things a little less stable. So, you know, it generates new problems, but the good news is that we've addressed them. And the punchline is that we end up with a method that can generate about the same quality of images as the slow process, but orders of magnitude faster. So this is a video that tries to show this. This is our model generating images on the right, while this is the old technique, just showing you how much faster our model is at generating things. And the quality is roughly similar. We lose a tiny little bit in diversity depending on the comparison we make. But essentially, so yeah, the old version, so this is with Stable Diffusion 1.5, was 1.4 seconds per image, and in this case we're at 0.05 seconds per image, so really much, much faster. And this is essentially, I mean, the acceleration is more or less the number of steps that you cut, because the cost of one step for us is essentially the same as one step for the original model. All right. Then I mentioned, so is that video also not playing? No, maybe this one is working. All right. As I mentioned, these techniques to generate new images from text description have been extended to the video domain. And I think that the first model that was really successful at creating convincing long enough segments of video was OpenAI Sora, which was a little more than a year ago now. I mean, it's really crazy how fast things are moving. Now, the challenges with Sora is that it is pretty slow to generate these videos. I mean, it was already problematic when you were generating individual still images, but now you're generating entire video segments, so speed is really a big issue. And the other issue for a number of application contexts is that these models are bidirectional, meaning that they generate the full segment at once, and they really need to take into account the full video segments. They cannot generate it frame by frame, so you can't do things in a causal manner, which prevents interactivity, right? There are many cases where you may want to look at, here are the past frames I've generated, now I'm going to generate the next frame, and I have no idea what will happen in the future, because maybe the user will tell me to change things. And the other advantage, of course, of generating things frame by frame is that you can start playing them before you're done with the whole thing. And so if you're a signal processing person, this means that these models are non-causal. They need to know about the future in order to generate something in the middle. And people had tried to generate videos in an autoregressive manner, in a causal manner, where all your model knows when generating a frame is past frames. But these models are typically not very stable because you end up with some drift. At frame n, you get a given quality, maybe a little bit of error, and then this error accumulates frame n plus 1 because it builds on frame n is a little worse than frame n, and by the time you've generated a full second of video, things look really like goo or whatever. And so my student, the same student, Tianwei, figured out how to address these issues, partially based on work by Professor Sitzman and Tedrick and their student on diffusion forcing. But really part of the idea is to train the model when you're generating a new frame to deal with potential errors in the past. And essentially, in a nutshell, the idea is that when you feed the past context to your model, say generate the new frame given these previous, say, 10 frames, you add intelligently a little bit of noise to these frames, essentially to get the model used to imperfect inputs. It's a form of regularization using noise addition, and this really dramatically stabilizes the process because now the model is used to fixing imperfect context inputs and can do much more stable generation of videos one frame at a time. I mean, another way to look at this general idea of adding noise to your inputs in situations like this is that you're essentially telling the model that, well, the input is not very reliable. You should use prior knowledge a little more. You know how videos look in general. You know how images look in general. Don't try too much to stick exactly to the previous context. Just keep in mind that things should still look natural and realistic. And furthermore, we use the same distillation ideas that I mentioned earlier, going from multi-step, many-step diffusion to single or few-step diffusion, which also dramatically improves the speed. And so we gain both in overall speed and throughput because of that distillation, and we gain a lot in latency because we can start, showing images as soon as we've generated the first frame. And so, if you look at the teacher model that we start with, you won't get to see anything before 219 seconds. With our model, after 1.3 seconds, we can start showing the video, and we can generate it at 9 frames per second. I don't remember what 9 frames per second. It's not a very high resolution, but still good enough to see what you're doing. So these are some of the videos you can generate like this. And again, here the input is just a piece of text saying, give me a snowman, give me a reindeer. So here are some of these pairs. So if you ask for a macro shot of a man wearing an antique diving helmet with dark glass and a jetpack working on the veins of a leaf, realistic style, the model somehow figures it out. And each of these frames, now my video compression is wrong. That's bad. If I want to show off the quality of my videos and the compression is messing everything up, that's not good. Right. This is another one, bunch of dogs. I mean, it's really incredible how fast this field is moving. I mean, as I said, really 2 years ago, you could just get, a second of video that was showing very little movement and that was quickly dissolving into goo. And now we can generate surprisingly realistic videos just, given a text as input. So again, I think we can really expect dramatic changes to the world of image making. I really think that this ability to generate videos either from scratch or from partial input is going to have a lot of impact. So this work was done in collaboration with Adobe Research. And as you may have heard, Adobe's already released some of these. In particular, I know people are using it to extend videos, like you have a B-roll video, but it's not quite long enough. You're missing a second or two at the end, so people really like to do that. Or maybe they want something slightly wider angle. So far, as far as I'm told, most of the use cases in the real world, at least for Adobe people, are like that. It's like you want a little more from footage you already have. But I'm pretty sure that in the not very distant future, you'll have a lot of video production that's going to be purely AI. I think in particular, kid cartoon video production will go through all the stages of the computer science and AI revolutions. I mean, it's moved largely from hand-drawn animations to now everything is 3D generated. So people really go through the trouble of creating 3D models and all this. But I mean, it's pretty clear to me that very soon all these videos will be done just with AI, because just creating 3D is still fairly expensive. And at least from my personal judgment, given the quality of some of these videos, it's not like the level of control that people want is really high. So I think what's going to be interesting is that unlike the 3D revolution, which really started at the high end, so the 3D revolution, I mean, one of the the big breakthroughs were Jurassic Park and Toy Story, of course, and that was like super high-end, enormous budgets and all this. And my prediction is that for generative AI, it's going to be more the mid to low end that's going to start using it, because you don't have as much control, which, like the Pixar people hate that. They've been saying for years and years, all we care about is control. We don't care about anything else. It's all about the storytelling and the ability to give the artist control over exactly what they want. So there's a lot of suspicion for the level of control that these approaches still can give. But I think at the low and mid end, it's a lot less important, and I think that's where it's going to happen. We got some good evaluations for some benchmark on videos, so we are very excited. The Adobe people have been deploying some of these models, the Firefly image model in their FAST incarnation uses the FAST algorithm I presented, and I think this is going to be deployed in a something based on these ideas will be deployed in the next generation or so, I believe. And very excitingly, we've been able to make one version of this video model open source, including the weights, and it's available at cosvid.github.io. And similarly, one of the two image models we developed is the fast image generation models is available open source, all the weights and all that, so that people can use them. All right, what else? So now, we've done images, we've done videos, and the really another frontier of all this generative AI for visual computing is 3D. And I'll mention one piece of work that we did with a bunch of faculty members and a former postdoc, Ayush Tiwari, on 3D diffusion models. So you have many cases where you want to recover 3D information from two-dimensional input. It's a very classic problem in computer vision, for example. So you have a 2D image and you want to output a 3D reconstruction. And this is very challenging, first of all, because it's a nilpotent problem. There may be multiple solutions. You're missing a bunch of the information. And so, this makes it natural to try to use machine learning and generative AI to learn the regularities of the world to make this problem solvable. And in particular, you'd want to use these diffusion models because they're very good at capturing the distribution of all the possible visual appearances in the world. And so it'd be great to use that to be able to generate 3D data given to the images. But a big challenge is that whereas it's really easy to capture 2D images with a camera, we don't have half as much 3D data out there. So we really have very little training data, which makes it hard to train these models. And so the goal of this work that we did was to bring the power of these diffusion models to 3D, but to be able to train them with only 2D data. So we want to learn something about the 3D world, even though all the input training data we have is 2D. And the main idea is still to rely on the 2D, on the diffusion process, but to have a strong inductive bias, meaning that we have a strong knowledge about how you go from a 3D model to a 2D image. So we carefully model, what happens when you have 3D data and you turn it into a 2D image, and you plug this idea in a diffusion model, and you learn to not only diffuse the 2D images, but to backpropagate all this all the way to the 3D data. And then, you learn how to generate these 3D images, these 3D representations, even though, all the training is at the level of 2D images with this process of inverse diffusion. And you get multiple big gains about this. One of them is that, now you can solve these inverse problems, but also you can deal with the uncertainty by providing not just, maybe one notion of the best output 3D reconstruction, but a distribution of 3D reconstructions. So this is an example where, given this input to the image, we can reconstruct these 4 different reconstructions, that have different opinions about what's invisible in the first image, all corresponding to the distribution of kitchens of 2D images of kitchens that the model had seen during training. And so, it's great to be able to explicitly deal with the uncertainty and get a sense of the distribution of outputs. And furthermore, each of these outputs is better than what you would get with a general reconstruction, because the way traditional methods deal with the uncertainty is essentially by saying, I don't really know, so I'm going to give you something blurry that's the average of all the possible reconstructions. And this is what happens when if you're familiar with minimum mean square reconstruction, that's the kind of phenomenon that happens where, if you want to minimize your potential error, you end up with something completely blurry because you just say, I don't know, it's something vaguely like this. And so, this is one comparison with one piece of previous work where you see really the previous work is really blurry, which is one way to convey uncertainty, I guess. But in contrast, we get nice and sharp images when the compression of PowerPoint doesn't mess up the images. Thank you, PowerPoint. It's cool because we can give you then some notion of variance of the reconstruction. So here it's color-coded. To tell you which parts of these reconstructions are more certain than others. All right. And I'll just advertise one more piece of work on 2D to 3D by my colleagues Justin Solomon and Vincent Sitzman and their student Artem Lukoyanov. Very, very related challenges, but in the case of text to 3D. So this is work on Dream Fusion at Google, one of the first pieces of work that tried to use denoising diffusion to generate 3D data from text. The big problem that they had was that they were generating a lot of blurry images related to the problem I just described. And essentially, I'll just show you a teaser for what they did, but essentially they have found a solution to generate very sharp and highly detailed images in state. And part of the trick is that when you do this kind of denoising, 2D denoising on 3D data, when you do the 2D denoising on multiple views, it's very likely that your noise is going to be inconsistent between the views, and that's going to really make the task very difficult. And again, the algorithm is going to say, well, this is all inconsistent. I'm going to give you something blurry. And they figured out how to use a 2D denoising process that's 3D consistent, thereby allowing the algorithm to generate much, much sharper results. Should I get you back on track, or should I keep going?
You're good.
All right. Sure. Just wondering if I show one more piece of work. I guess I have 7 minutes. Is that the official count? All right. So I'll just for fun, I'll show you one piece of work that I was involved in. It was very exciting because it's completely outside my normal area of expertise. Here we go. So this is work in collaboration with people in biological engineering on combining the delivery of vaccines with the recording of the information for patients. So, the big picture is that record keeping is very important in the healthcare area, but you have lots of parts of the world where you don't have the infrastructure to do that, and so that makes it very difficult. And in particular, we're interested in vaccine delivery, where when you do a booster campaign, you want to know who's already had the vaccine, when they had it, if there are any problems with the lots, you want to know who had a vaccine from what lot number, et cetera, et cetera. And so our colleagues in biological engineering, they've been interested in trying to keep this information on the patients themselves, which sounds a little crazy, but here we go. And so, they want to be able to come back to a person and just, be able to automatically figure out, yes, this person had the original vaccine 2 months ago. This is the brand of vaccine, et cetera, et cetera. And so the idea is to use the same delivery mechanism we used to deliver the vaccine to also leave an invisible record on the person's body. And so they have these microneedles. So the way they deliver the vaccine is you have a 10 by 10 array, something like this. I hope nobody has excessive needle phobia, but these are a lot of needles. And each of these needles has a little bit of the vaccine. That's how it's going to get into your body. And they add some markers that are invisible to the naked eye, but that can be decoded under a little bit of UV light. And some of these needles are going to be on, some of these needles are going to be off. And so the goal is after a few months, you come back, you use some regular camera with a little bit of exotic lighting, and then you can figure out which dots are on or off, and you get a binary code that can encode all this information that you're interested in. And they can even schedule how long the biomarker will stay, to make sure that after you're done with the booster campaign, people don't have those weird, as invisible as they may be, those weird dots on their body. Yes, there are lots of sensitivities around this issue of storing information on patients. They're very aware of this. It's led to a number of crazy theories because they were funded by the Gates Foundation. So if you've heard that Bill Gates was trying to implant chips to do mind control over people's bodies, that was part of the trigger. Anyway. Yes, it's been pretty exciting, and our role in this has been twofold. We've helped them with robustness, because, of course, people's bodies is not the most safe place to store information. So you worry about a lot of things. People may have small wounds or whatever that may make dots disappear. So we've helped them with error correcting codes. Essentially the same kind of stuff that's on CDs, if you remember CDs, to make sure that even if you lose some percentage of the dots, you can still reconstruct the full information, of course, at the cost of losing some storage capacity. And then, of course, we've helped them with the decoding phase, the computer vision algorithm that goes from these raw images to a bunch of bits at the end. And yeah, it's been tested on pigskins. As a computer scientist used to the speed of light of AI publications these days, it's been really eye-opening how long it takes to start some of these studies on animals and let alone on humans. They're planning to do a real study on humans, but this is taking a long time. But yeah, it's working pretty well. And to me, really the big question is, what are the real threats to robustness in the real world context? In particular, we work hard to do those error correcting codes so that even if you lose 10 of the dots, you still can recover the whole information. But one big question is, what are the usual problems that you'll encounter in the field, and how often will people lose essentially all the dots because, I don't know, you scratch yourself and then the whole part of the skin is gone. So I think really these are the big challenges for real world deployment in this case. All right, I will stop here on time. Thank you.